Okay, so I just did 1 point extra credit on number 2 part B, and as promised, if you want to fix your mistakes on a separate sheet of paper for number 1 and number 2A, go ahead and just fix those, do it on a separate piece of paper, and then tomorrow just make sure you hand me back both the quiz and the corrections. In the future, I will do a better job of making the quizzes do what I want to. Okay, anybody else need a 5.6 handout from yesterday about vectors? Okay. So if you weren't here yesterday, make sure you review the idea behind vectors, both the scalar multiplication by changing the length of a vector. If you multiply a vector by a negative number, it also changes the direction. Make sure you can, if you're given a couple of vectors, so actually just make sure you look through example 1 and example 3 in the textbook. That's what we went through. And then the other thing, and we're going to kind of use this today, but we have the, I guess I'm probably going to use, I guess you can use either one. You have the triangle rule or the parallelogram rule. And what that was is, for the triangle rule, if you want to add two vectors together, what you do is you take the first vector u, and then what you do is you place the tail of the second vector at the head of the first, so maybe that's the vector v. And if you want to add these together, the sum of u and v, that's supposed to be a new marker. Okay, there we go. U plus v would start at the tail of u and then finish at the head of v. Okay, so that's the triangle rule of addition. And then if I wanted to, say, add u and v, I'll do it this way this time. If I wanted to add u and v, oops, sorry, that's the wrong setup for parallelogram. If you want to add two vectors using the parallelogram rule, what you do is you join them together at their tails, okay, as opposed to placing the second vector at the head of the first vector. And then what you do is you just kind of translate v, so you get a copy of v up here, so that would also be the vector v. And then you can also translate u so that the tail of u is at the head of v. So here would be another copy of the vector u. And then starting from where the tails are joined, you're going to draw their sum to where the heads are joined. This would be u plus v. So we talked about the geometric concept of adding vectors with either the triangle rule or parallelogram rule. And then we, at the end of class, started talking about the components of vectors. And you can also, given the components of two vectors, you can add them together by adding components. So we're going to get to that today. So let me remind everybody where we left off. I did push play, I did. Okay, so I'm going to draw a picture here. So this is supposed to be the xy plane. That's the x-axis, that's the y-axis. So now we're talking about vector components and magnitude at the top of page 3. Okay, and the setup, I'm just going to draw a vector that's head is in the first quadrant for simplicity, but as you know, vectors can point in any direction and have any length. So a vector in standard position always has its tail at the origin, or if you like, I used initial side yesterday. So you can either call it the initial side or you can call it the tail of the vector. And so there's my vector v. Okay, in class you're going to see me write all these little arrow symbols, and I would like you to do the same on your homework or on the test. Reason being is, in the textbook they use bold-faced letters for vectors, but it's kind of hard when you're just using a single pen or pencil. It's hard to distinguish bold-faced from non-bold-faced. So I would ask that everybody uses these little arrows on top of their vectors. Okay, and then what you would do is say if the head of this vector is at the point v1, v2, Okay, so with the tail at the origin, the head of the vector, if the coordinates are v1, v2, you can write the vector in component form using angle brackets. Okay, the first component is just the x direction to get from the tail to the head, and the second component is just the y direction. Okay, so this is like how far left or right are you going, and that's how far up or down you're going, starting at the origin. Although you can really start at any point. Okay, but usually in standard position, the vector has its tail at the origin. And then we did an example sketching some vectors in the plane yesterday. I think we did 2, 6, -1, 3, -2, -4. So now what I want to talk about is, so we know how to draw them in the plane. I want to talk about the magnitude or length of a vector. Okay, so magnitude is just a word for the length. And let's see. Now your vector doesn't necessarily have to be in standard position. Okay, so what I'm going to say is given points P with coordinates x1, y1, and Q is going to have coordinates x2, y2. Okay. The magnitude or length of the vector, sorry, we're going to write PQ with an arrow. Okay, so first of all, I have to tell you what the components of the vector PQ is. Okay, this is the vector that starts with its tail at the point P and then has its head at the point Q. So let me draw a little picture here. So say here's the point P, has coordinates x1, y1. Up here, I have the point Q with coordinates x2, y2. And then this would be the vector starting at P and finishing at Q. Okay. And then if you like, you can draw in this little right triangle that'll help you see what the components are. And as a matter of fact, let me move this real quick. So Q, x2, y2. Over here, you're going to have P with coordinates x1, y1. So if I want the directions, the components are just the directions. How do I get from the tail to the head? Well, we just have to find the horizontal distance and the vertical distance. Okay, so if I'm starting here at the point x of 1 and I'm finishing over here at x coordinate x of 2, I can even write that down here. The distance right here is going to be x of 2 minus x of 1. Okay. And then same thing up here, I kind of ran out of room, but that's going to be the y coordinate y2. Right here would be the y coordinate y sub 1. And the vertical distance is just going to be the difference of the y coordinates. So, if you're going to write this vector in component form, the x direction is x of 2 minus x of 1. And the y component is y sub 2 minus y sub 1. So that's where that comes from. Oops. Okay. So if you're starting at P and finishing at Q, the first component is just the finishing x-coordinate minus the initial x-coordinate. And the y component is just the y component of Q, sorry, the y coordinate of Q minus the y coordinate of P. Okay. And the magnitude is defined by, so the magnitude or length of this vector PQ is, the symbol is going to be just like for absolute value. Okay, but I would like, in the case that you're working with vectors, we don't call it absolute value, we call it the length or the magnitude. Okay. And what it's going to be is, well, if I want the length of, this is just the hypotenuse of this right triangle. Okay. So the length of the hypotenuse squared is going to be the sum of the squares of the other two sides. So that's where this formula comes from. You're going to do x sub 2 minus x sub 1 squared plus y sub 2 minus y sub 1 squared. So that's just from the Pythagorean theorem. Okay. And then in the case where I take any vector in standard position. Again, this is v. The coordinates of this point are v1, v2. So the vector v would be in vector component form. V sub 1, v sub 2. In this case, if you're in standard position, the magnitude's the square root of v1 squared plus v2 squared. So you've got the vector between 2 points with its components and its magnitude. Or you can take the vector in standard position with its components, and then the magnitude's the square root of the sum of the squares of the components. This is all just coming from Pythagorean theorem. Okay. So we're going to calculate components and magnitude in our next example. Example 4, bottom of the page. So we're going to be given points. The origin is the point 0, 0. Maybe I can write a little sideways of O. And then we're going to have the point P with coordinates 3, minus 4, and the point Q with coordinates 2, 3. We're going to find the components and magnitudes of the following vectors. So we're going to look at PQ first. And then for part B, we'll look at the vector from the origin to P. Okay, so for part A, let's do the components of this vector first. Again, right, the components are just the directions. How do you get from the tail to the head of the vector? Right, you got to go some direction in the horizontal and some vertical direction. What you're going to do is the first component is going to be the x-coordinate of Q minus the x-coordinate of P. So we're going to do 2 minus 3 for your x component. And then the y component's just the difference of the y coordinates of the finishing point minus the initial point. So 3 minus negative 4. So the components would be minus 1 comma 7. So that would be the components of the vector with tail at P and head at Q. And if you want the length of the vector or the magnitude, the reason we call it magnitude is if your vector represents a force, like wind, or even if you're driving a car, your car is moving at a particular speed, that would be the force. So the reason we use magnitude is in the case that our vectors represent physical quantities like force or something like that. Okay. And now the magnitude or length of this vector is just going to be, well, I'm just going to use this formula right here. Okay. I almost never use this formula. Like, I use this formula to find the components, but once I know the x component and the y component, I just use this formula down here because it's the square root of the sum of the squares of the components. So that would give you the length of the vector. And let's see, we're going to get minus 1 squared is 1 plus 7 squared, which is 49. And we get the square root of 50. And that's, every time I have a chance to simplify something, I just do it out of habit. So the square root of 50 can be simplified. That's the square root of 2 times, well, let me do 25 times 2. So I'm finding the largest perfect square factor of 50, which is 25. And then finally, this would equal 5 squared of 2. Okay. So that would be the length of the vector, and the components are minus 1 comma 7.
So 5. So that's the length.
Yep, that's the length of the vector, yep. So anytime you put these bars on your vector, we're talking about the length or the magnitude. And if you say absolute value, I'll cringe. Okay. Okay. And then OP, so the components of the vector from the origin to P, this is a little bit easier because the origin has coordinates 0, 0. So in the case that your tail is at the origin, the coordinates of the point P just become the components of the vector itself. Right? Just like over here, right? the vector v starts at the origin and goes to the point v1, v2, those become the components of the vector. So I should just have 3 comma minus 4 if I want the vector from the origin going to the point P. So the coordinates of P are the same as the coordinates of the vector in the case that the tail is the origin. And then what do I do to get the length of that vector? So we take the square root, and then what goes underneath the square root?
3 squared plus negative 4 squared.
So we'll do the sum of the squares of the components. As Brandon said, 3 squared plus negative 4 squared. And this will be 9 plus 16, which is the square root of 25. So the length of the vector from the origin to P is just 5 units. Okay, everybody all right so far? Is there anyone here that's seen vectors before or had to because of maybe physics? I don't know, Rochelle, if you did vectors in physics at all. Kirsten, you've seen them a little bit?
Computer science.
Okay. So some people have seen them, some people haven't. That's why we're taking this approach from the ground up. I just assumed that none of us have seen vectors before, and I started from the beginning. Okay. Now, as you might have guessed, or you might have thought this to yourself, any vector in standard position, the vector can also be described by an angle from standard position, the positive x-axis. Right? So we can talk about this little angle theta right here, and we can find the components of the vector using the angle theta if you know the length of the vector itself. So that's the next example here. So let me come over here. So if you know the angle the vector makes with the positive x-axis, and you know the length of the vector, you can recover the components that way as well. So example 5, calculating components. So part A, this says, find the component form of a vector v. So find the vector v of length 6, pointing 60 degrees above the positive x-axis. As with vectors, anything with trigonometry, generally it's helpful to draw a picture. Okay, so what I'll do is draw a picture of this vector v. Okay, and let's see, I'll draw down this little, I'll draw a line that's perpendicular to the x-axis from the head of the vector. And this little angle right here is supposed to be 60 degrees. We also know the length of v, which is the hypotenuse, is 6. Okay. So this is just going to come down to triangle trig. Alright, so I'd like to find the components of the vector. Since the vector's in the first quadrant, the components are just going to be given by the base of this right triangle and the height of this right triangle. Okay. So for now, let me just call this A and let me call this B. And actually, I'll just draw, this is the vector V, and I know the length of that is 6. Okay, so if I want to find the x direction, I can solve for A. Well, if I'm trying to find A and I know the hypotenuse, what's a trig function I can apply to 60 degrees to relate the base to the hypotenuse? Okay, we can use cosine because cosine is the adjacent side over the hypotenuse. So we know cosine theta is cosine 60 degrees is going to equal the adjacent side over the hypotenuse, which has length 6. Right? The hypotenuse is just the magnitude or length of the vector. Okay, everybody okay so far? Everybody have a question on the setup? Okay. And then if you solve for A, you end up getting 6 cosine 60 degrees. 60 degrees is the same as pi over 3. Brady, you got a question?
Is there a reason we did like cosine A over 6 over sine B over 6?
We're going to do, I'm just finding this length first,
Just chose that way,
so,
just because.
well, we're going to find B as well.
So you just chose A just to do first.
Yep, I just chose to find A first. Since I know the hypotenuse and I'm trying to find A, we can apply cosine to get a relationship involving A and 6. And then like you said, when I try to find B, then we'll have to use sine. And then this is the same as 6 times 1/2, which equals 3. So cosine 60 degrees is 1/2. And then if I want to solve for B, you can apply sine to the 60 degree angle, and you'll get opposite over hypotenuse, so B over 6. So the y component, or the y coordinate of the head of that vector is going to be 6 sine of 60 degrees, which is 6 times root 3 over 2, which is 3 root 3. Again, 60 degrees is the same as pi over 3 radians. And I know for pi over 3 radians, cosine is 1/2 and sine is root 3 over 2. So that means the components of the vector v are 3 and 3 root 3.
So, sorry.
Yeah.
Test, do you want it in rate, like exact, or do you want it in decimal?
I generally, if it's a special angle, I want values exact. You know, if I gave you if I knew the angle is 72 degrees, then you'd have to use your calculator. Okay. So so that's a good question. Anytime you're doing sine or cosine of a special angle, I want the exact value. If you're doing sine or cosine of something like 71 degrees, 72 degrees, that's not a special angle. Then in that case, you have to use your calculator and get an approximation. Okay. So again, since 60 was a special angle, we should be able to find these values exactly. Okay, but anyways, those are the components. To get from the tail to the head, we have to go 3 units in the x direction, and we have to go 3 root 3 units up in the y direction to get to the head of the vector. So that would be our final answer for part A. Okay. All right. And then for part B, we got find the vector v, so the components of it, of length 10, pointing 15 degrees to the left of the positive y-axis. So again, let's draw a picture. So if we're pointing to the left of the positive y-axis and we're only doing it 15 degrees, we're going to have our vector in the second quadrant, and we're just saying this is a 15-degree angle. Right? So that's the positive y-axis. And that's the vector v. And what we know is the length of v, or the magnitude, is 10. Okay. So if I want the components of the vector v, I just need to figure out the x direction and figure out the y direction. Now first you're going to find the positive length of the base of this triangle, but really we're going to the in a negative direction, so we'd have to take minus this length. That'll be the first component. And then since we're going in the positive y direction, the height of the triangle will be the y component. Okay. Now if this angle is 15 degrees, the right triangle that I've formed has an inner angle down here of what? That should be 75 degrees. And if I, again, just like before, call this A and call this B, A is going to be 10 cosine of the 75 degrees, and B is going to be 10 sine of the 75 degrees. So it's the same argument before. I just cosine 75 is A over 10, so A is 10 cosine 75. And then sine of 75 is B over 10, and if you solve for B, you get 10 sine 75. Now this time, and this is why Chris's question was good, is 75 degrees a special angle? No, it's not 0, 30, 60, 90. It's not any of those angles that are multiples of 30, 60, or 45 degrees. So in this case, we have to get our calculators out. Make sure you're in degree mode.
Yeah.
And we'll just round them to 2 decimal places. 2.59.
9.66.
2.59.
Okay. And then the B is
9.66.
so the vector V, and here you have to be a little bit careful. So is the x component really going to be 2.59?
Going to be negative 2.59.
Yeah, since we're really going in the negative direction, we take the minus 2.59. And then 10 sine, well, we're going in the positive y direction, so the y component will be 9.66. And there's the vector v. Now, is this exactly correct? If we took the magnitude of that, we're not going to get exactly 10. We'll get approximately 10. Right? So this is an approximation. The vector v equals minus 10 cos 75 degrees, comma 10 sine 75 degrees. This is exact. And there's no way to, since cosine 75 and sine 75, those are irrational numbers. If you wanted your answer exact, you'd have to leave it in terms of sine and cosine. All right. How are we doing on time? We got 22. Okay, so I at least need to get through the next 2 examples so I can get through the last 3 examples in the first half of class on tomorrow. So let me come over here. So now we're just going to do some additional arithmetic of vectors using components and magnitudes. So vector operations in terms of components. Okay, so we saw before at the beginning of class you can add vectors or subtract vectors geometrically by using the triangle or parallelogram rule. There's also a way to add and subtract vectors just using the components. So if C is a scalar, so that just means a real number. Let's say the vector U has components U sub 1, U sub 2, and the vector V has components V sub 1, V sub 2. We can define the addition. So if I want to do U plus V, so you just add the x components of the vectors together, that gives you the first component, and then you add the y components together to get the second component. Okay, if I'm going to do u minus v, I can take the first component of u minus the first component of v, and the resulting component of u minus v would be u sub 1 minus v sub 1, and the second component would be u sub 2 minus v sub 2. So that's the addition, you add component-wise. That's the subtraction, you subtract component-wise. And then if you want to multiply a number by a vector, we already know that this changes the length and the direction. You just multiply each component by the scalar. So if I want c times a vector, I just multiply each component by c. So we're going to do some vector operations. So we're going to take u to be the vector with components 1, minus 1, 2. we'll take v to be the vector with components 2 and 4. And again, those components just tell us the direction from the tail to the head. So part A, we're going to find the magnitude of u plus v. Okay, so we're going to add the vectors together and then find the length. Okay. So I'll write u plus v in component form. So if I'm adding these vectors together, the x component's just going to be the sum of the x components. -1 plus 2 is +1. And then the y component is 2 plus 4, which is going to be 6. And again, the bars denote the length of the vector. And the length is always the square root of the sum of the squares of the components. So we're going to do 1 squared plus 6 squared, which will give you square root of 37. I'm just going to leave that exact as root 37. Okay, so there would be the length of u plus v. And then part B, we're going to find 3 times u minus 2 times v. So I'll rewrite both of these vectors in component form first. So I'll rewrite u as the vector with components -1, 2. And then I'll rewrite v with components 2 and 4. And then before we add or subtract those two vectors, we're going to use the scalar multiple property. So we'll multiply both components by 3 in the first vector to get -3, 6. So 3 times -1 gave me the x component, -3. 3 times 2 gave me the y component of 6. And then you have a choice here. You can distribute the -2 into here and just change the sign in the middle to a plus. Or what I'm going to do is I'm just going to multiply the +2 in here. So I have -4, 8. So I distributed the 2, or I multiplied by the scalar 2, and I left the minus out front. And then now, if you're going to subtract two vectors, the first component is just the difference of the x components. -3 minus 4, so you get a -7. And then the y components, you're going to do 6 minus 8. 6 minus 8 is -2. Okay. Any questions on those first two? All right. Okay. So part C is asking us to find two vectors parallel to v, so i.e. they have the same direction, but they're supposed to be half as long. Okay. So how do I get the vector half as long as v that's going in the same direction? So one would be 1/2 times the vector v. But there's another way to get a vector that's parallel, but not necessarily in the same direction. So do you see what I mean by parallel? Here's a vector. This is parallel. This is parallel. Okay, so one is 1/2 v, and Chris said the other is -1/2 times the vector v. So they're in opposite directions, but they're parallel to each other. They have the same slopes, basically. Okay, if you think of the vectors as part of a line, right, like you could extend the line through the vector, then they don't have to necessarily go in the same direction to be parallel. Okay? But they have to have the same slope if you think of them as part of a line. So 1/2 v is just taking our vector v with components 2, 4, and then multiplying in the scalar. 1/2 times 2 is 1, 1/2 times 4 is 2. And then actually, isn't minus 1/2 v just going in the opposite direction as the first vector? So really I can just multiply both these components by a negative. Okay? Or just multiply by negative 1/2. Negative 1/2 times 2 is negative 1. Negative 1/2 times 4 is minus 2. So those are two vectors that are parallel to v that are half as long. One going in the same direction, one going in the opposite direction. And there's, sorry, I'm trying to get through this. Like it might seem like I'm kind of flying. There's just lots of operations we have to talk about. So just to recap one more time, we talked about geometrically adding and subtracting vectors, parallelogram rule, triangle rule. Then we talked about the components as this being the direction to get from the tail to the head. Okay. And then we talked about how to find the length or magnitude, which is just the square root of the sum of the squares of the components. And then finally we talked about the operations component-wise. We can add vectors component-wise, subtract vectors component-wise. Multiplying a vector by a scalar is just multiplying each of the components by that scalar. Okay. So now we have essentially almost all of the operations. There's one more vector operation we're going to learn about, which is called the dot product. I might have to start that tomorrow, depending on how long this next example takes. Okay, so example 7, boat on a river. So now we're actually going to do a physical application. Vectors can actually be thought of either as a force, right, acting in a particular direction with a certain magnitude. Right? The force would be how hard you're pushing or pulling or something. You can also talk about vectors that represent speed in a direction. Right? If I start driving on Highway 12 at 60 miles per hour, that could be represented by a vector of length 60 going in the direction that I'm driving. Okay, and the same would be true here in this boat problem. So the setup here is a boat is going to be moving 10 miles per hour relative to the water. Okay, and there's going to be a 3 mile per hour current acting on the boat. So what I'm going to do is I'll draw this vector that's supposed to represent the speed of the boat. So maybe I can draw my little boat in here. Okay, there's my little boat right there. Okay, and it says the vector, or it says the speed of the boat is 10 miles per hour. And so the boat's going in a particular direction, and when we talk about speed, that's going to be the length of the vector. Okay. You could do this for airplanes as well, and thinking about wind acting on the airplane. And then what I'm going to assume is that straight up is going to be upstream into the river, and there's a 3 mile per hour current acting on the boat. Right? The boat might be going in this direction, but the current's going to push on you. It's kind of going to change your direction or your actual heading. So from the boat, what I'm going to do is I'm going to draw another vector, and I'm going to say it has length 3. Okay. So I'll say, and let's introduce some notation here. This is going to be, how do I want to write this? Well, let me do it this way. Let me call this VW for the velocity or speed of the boat relative to the water. And I'm going to call this a vector C for that's the vector representing the speed of the current. Okay. And I'll write this on the side. The magnitude of C is the speed of 3, and the magnitude of the velocity vector for the boat, that would be 10. So the boat is heading in this direction at a speed of 10 miles per hour. The current is acting on the boat straight down with a speed of 3 miles per hour. And then the problem is talking about an angle theta. That's where my angle theta is going to be. So from the positive y direction, the original heading or direction of the boat is given by that theta. And then it's saying, what does this angle have to be so that when the current acts on the boat, the actual direction is going to be perpendicular to the current. Okay, so I'm in my boat, I'm on the river, I apply some thrust or something like that, and I'm initially I apply the thrust in this direction. But because of the current, are you always going to keep going in that direction? The current's going to maybe kind of change your direction a little bit. The question is, what does this angle have to be so that, I guess, your ultimate direction in heading is going perpendicular to the current? Okay, so ultimately we want to be going in this direction. Let me think how I got to draw this here. There we go. And this is the vector we're looking for. It's going to be the velocity of the boat relative to the ground. Okay. So this is a physics application. Some of you might have heard in physics that if you have a force or a speed of an object and another force acting on it, the actual resulting force is going to be the sum of these two vectors, or the resulting speed and direction. So in this case, your actual vector giving you the new speed and direction is going to be the sum of the speed of the boat plus its direction. I guess so. We're going to take the initial direction vector, and then we're going to add the current vector. The resulting vector is going to give us the direction we're actually traveling. So the resulting direction is really just the sum of the two other vectors. One that's giving you the initial direction of the boat and the initial direction of the current. Okay. And then before I can find this vector VG, that's going to help me find this angle theta right here, I have to find the components of the vector C and the components of the vector VW. Now C is not too hard to find, because what's the x direction of the vector C if I'm thinking of it as going straight down? Yep, there's no horizontal direction, so the x component is 0. And then what about the y component? The speed is going to be the length of the vector. So the current's going 3 miles per hour, but is it going in the... It's going in the negative direction, so the y component's going to be -3. And then I have to draw a new picture to get the components of VW. Makes me think of Volkswagen. Okay, so I'm going to draw a picture for VW. So here's the vector VW. And I'm going to draw this little picture with this angle theta. So if I draw this little horizontal here, I now have a right triangle. I'm pulling that out. And the components are just going to be how far I'm going in the y direction and how far we're going in the x direction. So I have to find the length of this side and this side. Okay. So again, I can call this, I could call this A, if you like. But let's see, if I wanted to find this side, that's the adjacent side to the angle. Okay. So it's going to be 10 cosine theta, because cosine theta is going to be this length over the magnitude. And then if you multiply both sides by the magnitude, you'll get 10 cosine theta. And if this side's 10 cosine theta, anybody have a guess for the length of the other?
10 sine theta.
Yeah, that's going to be 10 sine of theta. So that's just coming from triangle trig. That's why I wrote it down real quick. If I apply cosine to this angle, I get this length divided by this length. And I can solve for the length of this side and get 10 cosine theta. If I apply sine to this angle, I get this length over this length. And if I solve for the length of this side, you get 10 sine theta. So the components of VW, the velocity relative to the water, are going to be, well, the x coordinate's 10 sine theta. Okay, that's the horizontal distance. The y coordinate's going to be 10 cosine theta. That's going to be your vertical distance. Okay. Check.
Got 4 minutes.
4 minutes? Perfect. Okay. So now the velocity of the boat relative to the ground, that's really the sum of the original speed and direction of the boat plus the current acting on the boat. That'll give us our resulting speed and direction. So we'll add those two vectors together. So I'm just adding components. 0 plus 10 sine theta is going to be 10 sine theta. And then negative 3 plus 10 cosine theta. Now, what was the condition? We wanted to find this angle theta so that the resulting direction was perpendicular to the current. So one of those two components would have to be 0, right? We're supposed to, at the end, the result is going to be going straight horizontal. So what would that mean about the vertical component? So look at this vector VG, it's going horizontal. There's no y component, right? We're just going in x direction.
Y is 0.
Yep. So this y component, this has to be 0. That's how we're going to get the angle theta. So we're going to set negative 3 plus 10 cosine theta equal to 0 and solve for theta. And we're going to do it in degrees. Alright, so if you solve this for cosine theta, you can add 3 to the right and then divide by 10. You'll get 3/10. And then what is theta going to be if I want to find the angle? So if I know cosine theta is 3/10, theta then has to be arc cosine of 3/10. I'll write cos inverse. What is it?
72.4. Or 54.
72.54 degrees? Okay. So what that means is if I wanted the boat to be going horizontally or perpendicular to the current, I'd have to start by going 10 miles per hour in this direction, where the angle right here is 72.54 degrees. If I start in that direction, the current is going to act on the boat, essentially turning me so that I'm going straight horizontal. So that's the idea there. And then now, what was the actual thing? We needed the angle and the speed of the boat. So now with that angle, VG is really just the x component is 10 sine 72.54 degrees, and the y component 0. So that gives me the resulting direction. And then the speed is the magnitude of that vector. The boat's going to be traveling in a speed of 10 sine 72.54 degrees squared. Because the other component is 0. So you just have to take the square root of the x component squared. But what happens when you take the square root of a square? They cancel or undo each other. So the speed is really just 10 sine 72.54 degrees. Anybody want to grab me that real quick?
9.54.
9.54? So it's going 9.54 miles per hour. Okay. There will certainly be 1 or 2 of these on the online homework. And am I out of time? Alright, so we'll have to finish dot product tomorrow. I'll try and get it done in the first half of class. The second half will be review. Thursday will be review. Friday is the exam.
Okay.
Alright, see everyone later.
Yeah, probably. I hope not.
Chris, I have a question.